Hello and welcome to this video on unimolecular nucleophilic substitution, or SN1. And in SN1 reactions, we can pretty much break it down into three steps. First, our leaving group leaves. The carbocation, which is formed when the leaving group leaves, is attacked by the nucleophile, which is usually weak, which is water in this case. And that extra hydrogen is lost. And I will explain that by going through each step one by one. So first off, let's show our leaving group leaving. So we have 2-bromopropane. So we have 2-bromopropane. The first thing that happens is it leaves. And that will form our carbocation, our secondary carbocation. And after our carbocation is formed, it will be attacked by our nucleophile. And our nucleophile in this case is water. So here's our carbocation. We have water, which looks something like this. Our two lone pairs. And our lone pair will attack that carbocation, which forms something that looks like this, with a positive charge on that oxygen. Now, these hydrogens, one of these hydrogens needs to be lost because this would be more stable like this, and having two hydrogens makes one of those hydrogens really acidic. So really all you have to know is we don't want this plus charge here. We want it to be gone, and the way we do that is by removing a hydrogen. So how are we going to do that? Well, we can do this. We can show our OH2 with our plus and another water molecule coming up and picking up that acidic hydrogen. So we'll do something like that. Move those lone pairs onto that oxygen so we get something that looks like this. And that is how we go from 2-bromopropane to this secondary alcohol. Now I'm going to explain the hybridization of sp2 and why that's important. Okay, now let's talk about the carbocation hybridization. This H3O plus right here, I didn't show it in that last little problem, was because it's not really important. What's important is this secondary alcohol. How I got hydronium is when I deprotonated that OH2. I took the proton off and put it on that water. That's how we got the H3O plus. But anyways, let's talk about this carbocation hybridization. As you can see, let me get rid of these two little things. As you can see, that our carbocation is sp2 hybridized. We have 1, 2, 3 sp2 hybrid orbitals and 1 p orbital. So carbocation is sp2 hybridized, and that is trigonal planar. So why is that important? Well, if we have our nucleophile, which was water in this case, we can attack from either the bottom or we can attack from the top. And if this molecule was chiral, which it's not because we have two of the same groups on this carbon, so it's not a chiral molecule, we would get a racemic mixture of both enantiomers. So we'd get a racemic mixture if this was chiral, so if chiral. Because we can attack from the bottom or we can attack from the top. Now let's look at a chiral molecule. Okay, now let's look at a chiral example for SN1. So, chiral SN1. Let's just use this molecule right here. Let's have a wedged bromine, a dashed methyl, and let's make a wedged methyl to make a chiral compound. And let's have our nucleophile be water. So what's the first thing that happens in SN1? Well, our leaving group leaves. So this will give us a sp2 hybridized molecule. And keep in mind our methyl group which was dashed here, is now just a straight line because we are trigonoplanar. Okay, now what do we do? Well, our electrophile is attacked by our nucleophile, which is water. Now, what did I say that was so important about sp2 hybridization? Well, we can attack from either the top or from the bottom, so that will give us a racemic mixture. So we'll have a racemic mixture when this molecule attacks from the top and then attacks from the bottom. So we'll have an alcohol that is wedged, and we will have a alcohol that is dashed, and a methyl that's wedged. Notice I did not mess with these wedges right here, these methyl groups, because we don't have our carbocation there. We have our carbocation here. That is why we are messing with the wedges and dashes on this carbon. Now, I did skip a step. I skipped the OH2, which we know has that plus on that oxygen, and we have to use another water molecule to get rid of one of those protons, and that would give us our alcohol. That is our answer right here. We have a racemic mixture of two of our tertiary alcohols. We have 1, 2, 3. These are tertiary alcohols. So let's look at okay, now let's look at some reaction conditions. So if we are dealing with a weak nucleophile, such as water or methanol, chances are we are doing an SN1 reaction. But of most importance is my second point, is the tertiary, secondary, and then those less than signs for primary is saying that that primary is not going to happen. It's not going to happen. Well, why is that? Well, this phenomenon called hyperconjugation, where that empty p orbital, which holds our positive charge, will be stabilized by those alkyl groups. They will share their electron density. So tertiary is the best, secondary is still good. Primary, no, it's not going to happen. Also, if we are dealing with a polar protic solvent with our nucleophile, that is going to be an SN1 reaction. Polar protic just means we have that hydrogen, such as water and methanol. Those would both be good examples. So yes, that does it for this video. I hoped everything was clear. If you have any questions, leave a comment down below. Subscribe, leave a like, and thanks for watching.